Temperature. Thermal physics, or thermodynamics, is the study of heat and temperature. Thermo means heat in Greek, and dynamics is the study of force. A physical object can change its temperature by addition or removal of heat, and by work being done on it or by it. Before the development of thermodynamics in the 19th century, heat was believed to be different from work. It was seen as a liquid called calor, meaning heat in Latin, that was transferred from hot to cold objects. This was not much different from how we understand heat today, except that it was not seen as being energy. The study of thermodynamics in the 19th century, mainly to understand steam engines, led physicists to understand that heat, like work, is a form of energy. Heat may be defined as non-mechanical transfer of energy due to a temperature difference. It is non-mechanical because it is not due to work done by a force acting through a distance. In thermodynamics, we will be very interested in the state of a system. The state of a system is its condition and is described by one or more quantities that specify it. In the microscopic view, the state at a given instant is the set of particle masses, positions, and velocities. In the macroscopic view, the state is specified by its macroscopic properties such as the number of particles n, temperature T, pressure P, and volume V. The systems we will study in thermodynamics have energy, but not the kind possessed by moving objects. Rather, they have internal energy, denoted as capital U, which in the microscopic view is the energy of motion of its particles. However, this motion averages to a static system that as a whole does not move. It has no bulk momentum or velocity or kinetic energy because its internal particles, while each possessing momentum, move in different directions such that the net momentum of the system is zero. We will now consider what happens when objects are placed in thermal contact. Thermal contact between two objects means that heat can flow between them. Matter that allows heat flow is a thermal conductor, and if it prevents heat flow, it is a thermal insulator. Consider two systems, A and B, initially isolated, that are placed in thermal contact. In general, the systems change their states and some of their properties, and after a while they both settle into states in which their properties don't change anymore and there is no heat flow between them. At this point, the two systems are in thermal equilibrium with each other. Equilibrium means balance. Now we look at the zeroth law of thermodynamics. Consider two systems, A and B, that are not in thermal contact. The zeroth law of thermodynamics states that if system A is in thermal equilibrium with a third system C, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system B, even if A and B are never in contact. If A and B do make thermal contact, they will immediately be in thermal equilibrium, there will be no heat exchange between them, and their states will not change. The zeroth law may appear to be obvious, but it is not. In the human sphere, if A is a friend of C and B is a friend of C, it does not necessarily follow that A and B will be friends. In physics, too, relationships do not always follow such a law. For example, if charge A is attracted to charge C, and charge B is attracted to charge C, it does not follow that charges A and B attract. In fact, the opposite is true. A and B will repel. The zeroth law of thermodynamics allows us to establish that two systems are in thermal equilibrium without having to be in thermal contact. However, they can also be in thermal contact, and when they are brought into thermal contact, there will be no heat flow between them. In this case, whether they are apart and in thermal equilibrium, or in contact and in thermal equilibrium, we say that A and B have the same temperature, T, so TA is equal to TB. This allows us to define temperature as any quantity that is the same for systems in thermal equilibrium. Temperature, in practice, is measured by a thermometer. A thermometer is a device that has a physical property called a thermometric property that varies linearly with temperature. For example, the height of a mercury column, resistance of a platinum wire, or pressure of a constant volume of gas. A mercury thermometer has a small reservoir of mercury that feeds a thin column of mercury. Its thermometric property is the volume of mercury, which changes with temperature and changes the height of the column. For the resistance thermometer, it is the resistance that varies with temperature, and for the constant volume gas thermometer, it is the pressure. Temperature is measured as a number on a scale. The centigrade scale, which we denote as T subscript C, is set by finding a thermometric property, let's call it X, at the ice point or freezing point of water, and at the steam point or boiling point of water. T is set to 0 degrees at the ice point and to 100 degrees at the steam point, and the range in between is divided into 100 equal steps, or degrees centigrade, written as little circle degrees C. Tc is a linear function of x. On the other hand, the Kelvin scale, denoted T subscript K, is related to Tc by Tk is equal to Tc plus 273.15. This Kelvin scale uses a single reference point, the triple point of water, which is the unique temperature at which water, ice, and vapor are all in phase equilibrium. These are the three phases of water: solid, liquid, and ice. And phase equilibrium is when there is no net exchange of matter between the three phases. This occurs at a unique fixed temperature. At the triple point, Tk is equal to 273.16 Kelvin. The unit is the Kelvin, capital K, which is not written with a degree sign. On this scale, there is an absolute zero temperature, below which T cannot go, so at this point T is equal to 0 Kelvin. The ice point is at 273.15 Kelvin, and the steam point is at 373.15 Kelvin. The pressure of an ideal gas is proportional to Tk, so we may use an ideal gas constant volume thermometer to define the Kelvin scale as Tk is equal to T at the triple point times the gas pressure divided by the gas pressure at the triple point. Now let's look at a couple of examples. The first example is a short example. What is the boiling point in Kelvin? We know that the boiling point in degrees centigrade is 100, and Tk is equal to 273.15 plus Tc, so it's equal to 373.15 Kelvin. Second example. A constant volume gas thermometer has P triple point equals 100 kilopascals. That's the pressure at the triple point. It measures the temperature of a liquid, and the pressure is equal to 80 kilopascals. Find Tk and Tc of the liquid. Well, Tk is equal to the temperature at the triple point, 273.16 Kelvin, times the pressure, 80, divided by the pressure at the triple point, 100. And doing that calculation, we get 218.53 Kelvin. Then Tc is equal to Tk minus 273.15, which is minus 54.62 degrees centigrade.